You're listening to Science Coast with Mallory Havens and
Chris White.
Welcome.
Today I want to talk about fusion energy. December 2022, there was a big announcement, a press release by the U.S. government, Department of Energy, about a breakthrough in fusion technology where they achieved what is referred to as ignition, where the energy released in the fusion reactions were greater than the energy used to initiate those fusion reactions. So there was a net energy output.
Which blows my mind because that's against, energy cannot be created or destroyed.
But it's sitting there waiting to be released. It's the same as the energy sitting in a Snickers bar. So it's chemical energy in a Snickers bar, and it's mass energy in the hydrogen isotopes that are going to be fused together. So the energy is released when the hydrogen fuses into helium. Mm-hmm. The mass of the helium is actually a little bit less than the mass of the individual constituents that go into making it. And that difference in mass is actually converted into energy in the form of kinetic energy, in the form of heat, effectively.
Right.
And this is how the sun creates its energy. So hydrogen in the sun is continuously being fused into helium. The helium nucleus, there's 4 nucleons, 2 protons, 2 neutrons. You take 4 protons, and then 2 of them get converted into neutrons. And when I take these 4 protons and 2 of them get converted into neutrons, and then I shove them all together into a nucleus, the combined mass of that nucleus is less than the mass of the 4 individual protons. And that difference is released in the form of energy. The energy is then transported from the core of the sun out to the surface of the sun, where it is converted into photons and radiates out to light up the world and power the earth through all sorts of, through means.
Light up the whole solar system.
Lighting up the whole solar system. Getting collected by plants to produce carbohydrates, which we can then eat. So the food that you're eating, the energy that's stored in those chemical bonds is actually coming from the fusion of the sun, fusion at the core of the sun.
Let me ask you a simplistic question.
All right, yeah, I'm going on. Sorry.
How does a proton become a neutron?
So it doesn't want to. So it has to be.
So the sun is torturing it.
Oh, it does. It does, absolutely. The conditions at the core of the sun are such that you don't give the protons a choice, and it becomes energetically favorable for the protons to switch over to a neutron. It's similar to a beta decay, but it's an inverse beta decay, where the proton will absorb an electron.
Okay. And
to maintain electric neutrality, it then will become a neutron, and the electron becomes a neutrino.
Oh, all right. Got it. And if you're listening and you're not super familiar, protons positive, electrons negative, neutrons,
thank you.
Neutrons neutral. I mean, I think scientists know that, but maybe not all of our listeners are.
No, it's good. I'm glad. And I'm always trying to check myself on things that I find, that's something which I know and I've known for a long time.
Right.
But it's not necessarily true that other people know it.
Right.
Back to the announcement, what they did in Lawrence Livermore National Laboratory out in California was to take a small pellet with milligrams of tritium and deuterium. Tritium is a hydrogen isotope where it's 1 proton and 2 neutrons. And deuterium is a hydrogen isotope that has 1 proton and 1 neutron. So there's 5 total nucleons. Between the 2 of those, there's 2 protons and 5 neutrons. If you can squeeze those nuclei together to the point where they basically start to touch, then the strong interaction, the nuclear interaction takes hold. And 2 neutrons, 2 of the neutrons plus the 2 protons will form the helium nucleus, and the 5th neutron is just shot out. It's like, we don't need you. Get out of here. And carries
poor guy.
Carries a significant amount of the energy of the fusion process. So the key is, since the 2 isotopes are both positively charged, they don't want to get very close to each other. They're repelling each other.
Right.
So the only way that you can get them up close is to get them very, very hot and get them very, very under very high pressure. In order to get them very hot, and we're talking 100 million degrees Celsius, and to get them close to each other to create the high pressures necessary, they blast this small cylinder cube of deuterium and tritium with lasers in a way that it implodes. It creates an implosion. And in the process, and it's called inertial confinement. So you basically are shooting it with an enormous amount of energy from the outside. You hit it as uniformly as you can around all angles, and it takes that sphere and compresses it to about 10 times the density of lead.
Okay.
While also increasing its temperature literally into the tens or hundreds of millions of degrees Celsius.
What kind of facility do you have to do this?
A national laboratory.
Well, yeah, is
where
it like
you have a dedicated facility, and this is big science. This is big science where the government is investing millions and millions of dollars to create this its apparatus. Is effectively what it is. It's an apparatus.
Why would the government want to do that?
Well, one would hope that we wish to develop fusion technologies so that we can have what is referred to as carbon neutral energy sources. If we can, even if it takes a lot of energy and if it takes a lot of infrastructure to create this explosion, if we can then harvest the energy created, presumably heat up water, drive some turbines, generate some electricity, the net effect may be better long-term for society than continuing to burn coal and natural gas to generate electricity with.
Why is it better than nuclear power?
Oh, good question. What's the difference between fission and fusion? For the fusion processes, we're taking small nuclei and squeezing them together to make bigger nuclei. You're taking individual hydrogen and squeezing them together to make helium. In the fission processes, we're taking extremely large nuclei, breaking them into smaller pieces, and in the process releasing energy. So the most efficient, if you think about it that way, the most efficient nucleus is iron.
Okay.
So as you squeeze elements that are smaller than iron, fewer nucleons than iron, you will get energy out up until the point that you actually get to iron. When you make any of the elements that have more nucleons than iron does, you have to add energy in order to make those nuclei. So if I take something like uranium that has 238 typically nucleons inside of it, and I break it into smaller pieces, what will typically happen is that energy would then be released in the process. So fusion processes take very heavy elements, break them into smaller pieces, that you create an environment in which they will do so. Typically, you have to hit them with a neutron, and the neutron causes the nucleus in some sense to break. You're literally splitting atoms. That is literally the definition of splitting atoms. The problem is that those smaller pieces that the U-238 breaks into, and it's not actually U-238, it's fissile like U-235. But anyway, the smaller pieces are radioactive.
So it's a waste problem.
It's a waste problem. That's right. So when you're done getting the energy out of the fission reaction, you now have all of this highly radioactive stuff.
Which is why I'm not a huge fan of nuclear energy.
Like Fukushima.
That and like Yakima Mountain, and like what do you do with all the waste, you know?
Exactly.
So you're saying fission and fusion doesn't have waste and fission has waste.
Yes, the core byproduct of fusion processes will be helium.
So we can fill all the balloons?
Yes.
Yes. Finally. Because helium's so hard to store.
And there's a finite quantity of it. It's actually a national resource.
Yeah, they store it underground.
And that's where it comes from. If helium actually gets into the atmosphere, it will escape.
Right.
It gets to the top of the atmosphere, and just like your balloon floats up into the atmosphere when you let it go, the helium, after it gets out of the balloon, also will float up to the top of the atmosphere. And then through interactions of photons coming from the sun, it will then reach escape velocity, and then boop, it's gone. That's why there's no helium in the atmosphere itself. If we want helium, we have to go get it out of the ground.
Right.
Mine it. It's really strange that you go mine this gas out of the ground. And it turns out that the helium that's in the ground that we mine is from alpha decay associated with heavy elements that are undergoing radioactive decay.
Yeah. And if you inhale helium, you get a funny voice.
Do you know why?
I'm assuming just because of the density of the gas. No.
In the voice box. No, yeah, it is. So what you're doing is you're changing the speed of sound in the airways.
Right.
So that it impacts, the speed of sound is related to the frequency of the wave that's being generated. So if you want to change the frequency of the sound coming out of your voice box, you can't change the physical dimension. The wavelengths are fixed because you have a physical dimension associated with your anatomy. But if the speed of sound changes, then the frequency changes, and frequency, of course, is pitch.
Right.
So another physics lesson.
Learning so much today. So the government wants to do it theoretically to have a carbon neutral energy source. Is that what the government...
Well, you said the government wants that. I think that's what I want. I think that's what society wants.
Okay, yeah. What does the government want?
So I printed out the press release, and the press release talks about how the agency associated with this breakthrough is the National Nuclear Security Administration, NNSA. And all you have to do is Google DOE, Fusion, press release. They're not lying. They tell you that it is associated with the National Nuclear Security Administration. That's the agency that did this research. So then the question is, well, who is the NNSA? Well, the NNSA was established by Congress around the year 2000 as a semi-autonomous agency. And whenever I read semi-autonomous, when it's associated with the government, I'm like, uh-oh.
CIA.
Uh-oh. So it's within the U.S. Department of Energy, responsible for enhancing national security through the military application of nuclear science. So I'll say that one more time. Enhancing national security through the military application of nuclear science. So it turns out that when you do a little bit of digging below the surface, this technological breakthrough is in fact part of our weapons program. What they in fact did was create a miniature fusion explosion, just like what happened in our nuclear arsenal bombs. So I have a little bit of a story, if it's okay with you.
Yeah. Are we going down conspiracy theory lane? I'm just kidding.
Absolutely not.
Oh, okay.
Absolutely not.
Good.
Back in the late 20th century, the American government made some armed controls agreements, which I'm in favor of, with the Soviets, basically saying that we're going to stop testing nuclear weapons.
Right.
And the military was concerned because what they would do is they had this large stockpile of atomic weapons, and literally they would periodically pick one, to send somebody into the arsenal, just bring us back an atomic bomb. And they would pick one out of the arsenal, they would take it to Nevada or some other location, bury it deep under the earth, and
blow it up.
And then they would have lots of sensors to make sure that the yield and the bomb exploded exactly in the way that they expected it to. So this was a way of ensuring that the arsenal was viable.
Right.
So that if the U.S. government ever needed them, they would know that they were reliable and could count on the bombs working. Well, they could no longer do that because of the arms control agreement.
Right.
So then they decided, well, the next best thing for us to do is to create simulations to be able to write computer code that would allow us to feel confident that as this arsenal ages, it still is reliable and will still work. If you wish to develop computer simulation, you have to test it against experimental data.
Right.
So this experiment was about using simulation to predict what would happen under certain scenarios and then verify that that actually happens.
Do we still make nuclear weapons, or we just have our arsenal that is stagnant?
I don't know if we need to. I think
we did make a lot.
We made a lot. That's right. Starting back in the 1940s and 50s, we started producing and building our arsenal. I believe at some point, I'm not an expert on this, I believe at some point we had so many that it was overkill in some sense. There was more than...
It was enough to nuke the whole planet.
Seriously.
Yeah.
Seriously.
I know, yeah.
I actually had a friend once, colleague, who I worked with, who had been part of that program. And one day, whether it's true or not, I can't confirm, but he actually told me this. If you wanted to end life in the Northern Hemisphere, you don't actually have to send the arsenal on rockets to blow up other countries. You would just have to light them all off simultaneously, even in the U.S. And so if you took the entire U.S. arsenal that existed back in like the 80s and 90s, and it just basically detonated every atomic bomb that we had, where it was, the consequences to the atmosphere would be so damaging that it would probably end human life in the Northern Hemisphere by itself. So you don't actually have to go blow up the cities. You just have to detonate the weapons. And the damage generated there's so much downwind damage that is done that it would end life.
Nuclear warfare is just horrifying. I'm really glad that, this is not commonly frequently used or, hasn't. It's just such a... The fact that they would teach kids, if you see the bomb drop during the Cold War, like, hide under your desk. Like, what is the point? If you see the mushroom cloud, you're done.
That's actually true. I've thought about this a lot myself, and if there ever was going to be a nuclear exchange, I probably would not want to survive the first round.
Oh, yeah. No, my parents, again, because they didn't really know what was child appropriate and not, would tell me if I ever saw the mushroom cloud, I should walk towards it to just get it over faster.
I would hate to think that this is how we're going to end this session.
Oh, no. So we've all agreed that nuclear warfare is a bad idea, and governments are hopefully not going to do that.
You know what we should do? We should do another podcast about the research that's going on to create fusion energies to generate electricity and decrease our carbon footprint.
Instead of what was really happening, testing our nukes.
Well, that research is in fact happening, and there is some hope that before the end of the century, we'll have the technologies to generate electricity using fusion, so that we can reduce our carbon footprint and we don't have to have all that radioactive waste associated with the fission reactors. But that's a different topic, and that isn't what happened back in December, and that wasn't the program that was being promoted through all the various news outlets starting in December.
Well, a talk for another day. Disclaimer time.
Oh, I can't wait. I love disclaimers.
The views, thoughts, and opinions expressed are the speaker's own and do not represent the views, thoughts, and opinions of Lewis University. The material and information presented here is for general information purposes only. The Lewis University name and all forms and abbreviations are the property of its owner, and its use does not imply endorsement of or opposition to any specific organization, product, or service. This podcast was produced in the WLRA podcast studios at Lewis University. Visit lewisu.edu for more information about Lewis University. And you've been listening to Science Coast with Mallory Havens and
Chris White.
See you next time.
Bye.